All right,
Did you draw that?
I did.
You couldn't tell at all.
Really? I thought it was generated by the axis. Is so straight.
The axis-
You did a really good job on that.
Actually, the practice is not too bad.
It was a little later at night when I did the other one. All
I
right.
had a lot of coffee.
Yeah, it actually was early this morning. It was so.
You just said late last night.
I know it was loud.
Thanks.
Well, late last night would be this early this morning.
Yeah, I was gonna say, how late were you up last night? 3 o'clock?
Oh, just my typical getting ready for.
Calculus.
He
doesn't sleep.
Two.
I'm so
2 in the morning. All right. Number 3, please. If you would open your books. 420. Now, what I want to emphasize about the homework here is a couple things. Number 3, number 10, and if there's something else you want to talk about, we can. But in number 3, when we have our test that involves these areas, now it involves all the things from chapter 7, so it'll be a variety of these problems. But you have to be able to identify the correct region. I will not, and not that this comes as any surprise to you that I will not help you on the test, but you know, if the problem is worded like 3A, you know, you have to be able to identify, you have to be able to graph the graph, either by hand or with the calculator. Now on the quiz on chapter 7, I think we will be allowed to use a calculator on the whole thing. So if you need the calculator to draw a graph, you can do that. Now, on this particular problem, number 3, you know, the curve, one of the curves is given as this, and one of the curves is given as x equals, is it 2 plus y? Y plus 2, x equals y plus 2, right? And then y equals 1, y equals -1, another horizontal line, and so forth. Now both of those are given in ways we're not used to. We're used to seeing y equals. Of course, this would lead you to think which kind of strips? Horizontal strips, which I told you back on page 415, where this picture was drawn for you, that they went ahead and worked it with horizontal strips, because that's clearly what you would choose to do if you had a choice, right? So on the quiz, if I said find this yellow region, right, which is this region right in here, okay, and of course the quiz probably will not be in color, but it will identify, it will say the region bound by x equals 1 minus y squared, and it might say like they did on the left and on the right, or it may not. In other words, this one wouldn't have to. If it just said find the area of the region bounded by x equals 1 minus y squared, x equals y plus 2, y equals 1, and y equals -1, there's only one possible region that is bounded by all 4 of those things. It's this region right here. So, okay, if the problem is worded correctly, there should only be one possible region that fits the description. You have to be able to identify that. And you have to be able to draw those graphs. Now, of course, we know that to put them into our calculator, we need y equals, right? So we would solve this for y, and this is what you should have done for parts A, B, C, and D here. I'm going to go ahead and just do it right away here. I'm going to solve this for y, which gives me plus or minus, which of course gives me the top and the bottom half of the parabola. So when you put that into your calculator, it's 2 separate graphs. It'll graph them for you. And then also, the other one would be y equals 2, x minus 2. Okay, so you could graph those, and you could graph y equals 1, y equals -1. You can't really graph vertical lines. There's a draw feature that you can do, or you could try to fool it by making a slope of 1,000,000, you know, and get an almost vertical line, you know. But typically, it's not really necessary to put in the vertical lines on your calculator. So you would want to do something like this. All right, now, horizontal strips would work best because if I put a horizontal strip in here it's going to touch the line on the right side all the time, and it's going to touch the parabola on the left side all the time. Do it right minus left, and that would be the easiest way to do it. That's how they did it. They got 8/3 for the answer. What you were supposed to do in problem 3 is take the regions they identified, and you were supposed to do vertical strips. Now, I think I was fairly clear on my directions of that yesterday. So let's read that and see if we can understand that. So in 3A it says, find the area of the region bounded below by the x-axis, let's do this in red, below by the x-axis, so that's the bottom boundary, above by y equals 1, so here's the top boundary, on the right by x equals 1, which would be this line right here, x equals 1, and on the left by the parabola. Well, that is this region right here. And you were supposed to use a vertical strip. So, we do a top minus bottom. So the integral would go from what to what? 0 to 1. The height of the strip is the top y coordinate, which is what? 1, minus the bottom y coordinate. What's the bottom y coordinate? The top half of the parabola, which is positive square root 1 minus x. And then the width of the strip is dx. So we got the height of the strip is this, times the width of the strip, that's the area of the strip. The integral then adds up all the strips. And we get what for the answer? It is 1/3. Okay? In blue, part B. B for blue. Bounded above by the x-axis, below by y equals -1, on the right by x equals 1, and on the left by the parabola. Well, that's this region down here. Now, you can probably guess that's going to be 1/3. But I'm not interested in 1/3, I'm interested in your integral set. So the integral would go from 0 to 1, a vertical strip, top y coordinate is the negative square root, which is the bottom half of the parabola, minus the bottom y coordinate, -1, change that to add the opposite, with dx, there's your integral, and of course you type that in and you get 1/3. Part C, put that in green. Well done. All right. Part C, find the area bounded. Now notice this doesn't say above and below and left and right, but it doesn't have to. Find the area of the region bounded by the line x equals 1, which is this red line, by this line here, and by y equals 1. Now if you look at that carefully, this is the only region that is bounded by all three of those things. Y equals 1, x equals 1, and this line here. They didn't have to say y equals -1 because they cross right here, okay, and they didn't need to say it. So that's it. Now it's a triangle. You could just calculate the triangle, but not really. If this was on the quiz, you have to set up the integral. That's what the directions are for. That's what I'm looking for. We put a vertical strip in there. Top y coordinate is 1 minus the bottom y coordinate, the line, which would be this right here, x minus 2. Width is dx. Strips go from 1 to 3. You type that in and you get 2. You add up those areas, 2 2/3, which is 8/3. Now, if you had a choice, you would not have chosen to do it that way. Okay? You would have chosen to do what they did, which was a horizontal strip, do it in one integral. On the quiz, you probably most of the time have the choice. Just find the area, you use whatever strips you want. Probably set it up so one time horizontal strips will work best, one time vertical. Or I may just say, hey, you have to use vertical strips. Now, remember those problems we've been skipping? About solids and revolving, right, and so forth? Those are also going to involve this right minus left, top minus bottom using strips. So understanding this concept of getting this integral set up is really important. And I think once you get the hang of it, it's pretty easy, really. I mean, I think if you had to compare these problems to chapter 4, you know, the optimization, setting those up, some of those things, I think they're easier now. Part of that's because you're just better now. Some of it is because I just think they are a little easier to understand. Okay? All right, number 10. Number 10 kind of changed direction a little bit, just talking about this thing of idea of units. Now, so I won't spend a lot of time talking about this, but the idea is if you have the integral from 1 to 3 of f, that if f is some rate of change, then the integral is what? Amount of change, net amount of change, net amount of change. So in part A, if f is velocity upward in feet per second, then this integral is what? Distance, feet, net feet traveling in what direction? Up. That would be the net change in upward distance. Okay, and if it's negative, it would mean what?
Down.
Went down. Okay? Part B, if f is acceleration in feet per second, then what's this integral? Net change in velocity, feet per second. Net change in velocity, feet per second. C, net rate of flow of water into a tank in liters per minute. If f is liters per minute, then this integral is net liters, net change in liters. So if it's positive, gained water. If it's negative, lost water. Okay? And then if f is the slope of a graph, what's this integral represent? Well, hard to think of because you don't have units. Think of it as rise over run. Slope is the change in the rise, basically. So it would be the net change in rise. In other words, the net amount that the graph goes up or down. If it's negative, it went down. If it's positive, it went up. But it'd be the net amount of change in the rise of the graph, because that's what slope measures, is how fast a slope goes up or down. So the integral of that would be the net amount of change that the graph went up or down. Imagine if the graph was the flow of water, right? Then we just said it's a net gain or loss of water. Okay, well, the graph of the amount of water would go up and down, right? And so if it went up, it was a net gain. So, all right, anything else on that? Any of those other ones you wanted to look at? 17 and 23 were doing the regions. You had to graph them yourself, the whole thing. You needed to have pictures. If you just had integrals set up, that's not good enough. You need to really have pictures drawn anytime we do these. And, well, it did say it. It said sketch a region. And then 29 and 35 was the same regions with horizontal strips. We've got time if you want to see one, but 23, both parts, like the vertical and the horizontal. I mean, once we have it set up, it's pretty easy. And you wouldn't have to draw two pictures. You wouldn't have to, okay. Once you have the picture for 23. Uh-oh. Oh, no. It's kind of fun. All right, 23. X equals y squared minus 4. Y equals 2 minus x. Okay? So, since I know I'm going to be doing both vertical and horizontal strips, I would probably go ahead and solve them right away. So I got y squared would equal x plus 4. Y would equal plus or minus square root x plus 4. Normally I wouldn't do that. I would first decide, well, I would do that on this one because I need to graph it anyway. Now, you might be able to look at that and say, hey, that's a sideways parabola. Okay? Now, tell me something about this sideways parabola here. What's the minus 4 do on a sideways parabola? You know, a regular graph, it shifts it down. That would be a left shift, right? A -4 would actually be a left shift, because those shifts then are different when you're talking about these x equals type equations. So this is going to be a sideways parabola shifted left 4. Okay, now you could look at this over here and say, well, that's a square root graph, which of course is the top half of a parabola shifted left 4 as well. So you can see the same idea, and it's both halves. Now, if I put in a 0 for x, I get square root of 4 plus or minus, that'd be 2, -2. So here would be my parabola, like so. And then this would be a 2 intercept and a slope of 1, -1. Do that right?
Should intersect it.
It should intersect right here. We can fix that. There we go. All right. So, there's my picture. So clearly, we're talking about this region. That's the only possible region that would do that. All right, so for part 23, in the blue, let's do vertical strips. Now, when you're going to do vertical strips on this one, what are you going to have? What are you going to have to do? 2 sections, right? You're going to have to divide this right there, because a vertical strip over here is going to touch the top and bottom there. A vertical strip over here is going to touch the line and the parabola. You're going to have 2 sections. So, our first integral.
Is that what in the pocket? He reached for it and spoke from his pocket.
Alright. So, what's this first integral do? What to what? -4 to 0. The strips fill the space from -4 to 0. Top y coordinate is the top of the parabola, square root x plus 4, minus the bottom half of the parabola, negative square root x plus 4, which of course just makes 2 square root x plus 4, with delta x dx. Plus, the second integral is the line, y coordinate, which is 2 minus x, minus the bottom half of the parabola, negative square root x plus 4. Change that to add, that would be dx, and that goes from 0 to 5. Because down here is the 0.5 and -3. Add up all those, and we get 125. Doesn't that sound familiar? Yeah, probably. Isn't this that same problem we said we had an upside down parabola? We had a line coming through it, right? It was the same thing, it was the inverses of these 2 functions. I think we had x equals 2 minus y, and we had y equals x squared minus 4. Matter of fact, some years, I've had some people who, when they get this x equals y squared minus 4, they will just interchange the x and the y, and they'll do y equals x squared minus 4 and graph it. And then they'll do the inverse of this one. They'll then make this one x equals 2 minus y and solve for y because it's easier. Now, is that okay? Well, obviously we just showed with this, if you take this picture and do its inverse, you'd have an upside down parabola here, and you have a line coming here, right? You end up with that same region. Now, that's not the right, you're not going to get the point, so, because when it says sketch this region, that inverse region is not the same region. It has the same area, but it's not the same region, because they're not the same graph. So, I mean, it does work for getting a final answer, but you really need to be able to graph what's given. All right, so there's 23. 35 is easier, because 35 just takes one set of strips. Even though it looks like 2. Just make it a little thicker. Okay. One horizontal strip will do it, because a horizontal strip touches a line on the right every time, touches a parabola on the left every time. So it's your right x coordinate, which is, I didn't do that one, I guess. Add the x over, subtract the y, x equals 2 minus y. So the right x coordinate is 2 minus y. minus the left x-coordinate, which is this parabola. Put it in parentheses, y squared minus 4, dy, because the width is a change in y, and that goes from where to where? The strips fill the space. You always go from little up to big. The strips fill the space down here from -3 up to 2. -3 to 2. And if you type that in, you better get 125. We have found something wrong with calculus. All right. Okay, so if you have a choice, you kind of pick which one might work best, horizontal versus vertical. Do both to check. I've had people do that on quizzes if you have time. Yes.
Are you gonna like choose which one we have to do?
Yeah, I may say do this with horizontal strips, or I may just let you choose, or I may do both. Okay, I may pick one that's could be done easily both ways, or I may pick one that clearly would be best with horizontal strips if I want you to do horizontal strips. But like I was saying, when we do the volume stuff, we do some of the other stuff in Chapter 7, you're going to have to do the strip thing, horizontal, vertical strips. So you'll get plenty of practice at being able to do one or the other. So you really need to understand both. Okay, let's do one more thing here in section 7.1 that we skipped yesterday. Okay, so you might want to jot this down in your notes here today. Here's going to be all right, section 7.1 actually had two concepts in it. One was the length of the curve, or excuse me, one was the area between two curves. Okay, and the second concept is finding the length of a curve, finding the arc length, if you will. Those two things are interchangeable. So this would be the problem that we are going to pose here. Find the length of the curve y equals 4 minus x squared from x equals -1 to x equals 1.5. Okay? So first let's draw a quick sketch of that. Go ahead. What would it look like? On your paper, draw a quick sketch. What are you drawing? Anybody? Parabola? Upside down? Up 4. Cross the x-axis at 2 and -2. Right? Very similar to the sideways parabola we just graphed a minute. Right? All right, and so I've got a picture of that here. Okay? And so what we would like to do is find the length, and they call it arc length of a curve or arc length, same thing. We want to find how long this curve is from there to there. Now, what is the issue? What is the problem with doing that? It's hard. It's hard. It's curved. Yes?
How do you straighten it?
Well, you know, if this was on a piece of paper in front of me, I mean, if I had a piece of string, right, I might set a piece of string along there, try to get it to fit just so, and then straighten it to measure it, right? Because we can measure straight things, but we can't really measure curved things.
Well, can you find the area and then like straighten it and then say like you know the two heights and set it equal to the area and then solve for the
The only part you're losing me on is where you say straighten it. You mean just stay right here at 4 and just,
No, like, you would stretch it out, so It would
you're
have the
losing me
same
there,
area.
how am I gonna stretch it out?
just like in your mind, like.
Okay, just
We're all
imagine, kinda like we did average value, in other words, there'd be this area under here, from here to here, and then imagine another line here somewhere that would have that same piece of area or something?
Yeah, but it would be stretched out because, like, the,
So it wouldn't go from 1 to -1 to 1.5?
yeah, exactly, it would be longer.
Find the area and make it a rectangle.
Yeah,
Right, I'm with you, and so what you're saying is if I found this piece of area here,
uh-huh,
or you talk about this area if I connect,
no,
okay, you're talking about this area here.
uh-huh,
Find a rectangle, but here's where I still think there's two unknowns. Find a rectangle that would have that same area,
yeah.
right? But I guess as I try to imagine it, I don't know how wide to make it, and I don't think I know how tall to make it. I know what area I want, because it's this area. But I don't know that I know either of those two things. That would give me a lot of possibility.
You have the two sides, so you can make the,
Not triangle, just pull it. With those two sides.
Yeah.
Pull it all.
So it'd be a trap
straight.
So connect this here, is what you're saying?
but
No,
then
like
you
with
would
the
lose
area.
area.
So you just have to.
No, but then stretch it out. Is that what you're saying?
I wanna say stretch it out until you
Stretch it out.
I'm saying the straight.
I'm just not sure what you mean by stretch. I'm still
Put an
not.
octagon.
We should draw a picture.
Yeah, you wanna draw a picture?
I mean,
I like your African.
Go to the board.
okay, we've got an area there, a known area. Let's say it's 30.
Well,
Make the shape of the parabola.
You can.
But,
He's drawing you.
cause what you said about the two unknowns, I realized, like, once you stretch it out, you'll have that bottom, but then the top won't be the same size as the bottom. But then could you add the length over to the other side? Like, cause A is taller than B,
average them?
could you, yeah, average them and then?
So you're saying go from here to make a rectangle?
No,
In
like,
the middle of them.
go
In the middle of
yeah.
Okay, so in here somewhere.
So
make
you
a-
know the height if you average the F.
So I just went the midpoint between this y value and this y value, went halfway.
Yeah.
So we know that height.
And
And
then you have the heights.
And then
you
divide
have
the area. So take the area divided by this height, this height right here, and that would give me a length.
Oh, but it wouldn't be the same.
I don't think so, because I think if I just do the mid, like you said, average, which would be the midpoint between here and here, what if this went way up and came back down to here? You'd have more area under there, but yet you'd still have that same average, right? There'd still be that same average, right? And there'd be more length. If this went way, way up and came back down to these same points, you'd have more area, which would give you more length here. Excuse me, well, then wait a minute. If you go way up and way down, they give you more area, but then if you divide by this same number here, you get a bigger length.
Yeah.
Teach us on this.
Well, no, I'm interested in this idea. We might try that when we're done and see if we get the same answer.
Let's do it.
Well, is there,
I don't know.
Let's do it.
Let me,
the first way I was thinking of it was like kind of a trapezoid-ish,
okay,
you know? But I don't think that would work because.
but we might do the rectangle thing, but no, I'm curious. But let me show you the way I thought of doing it.
You came up with it?
I did, yeah, I did. It was funny, and then they happened to have it in the book too, which was
Oh, that's
coincidence.
strange.
So the, if we go back to every main idea that we learned this year, and I think I've said this before, that we could really summarize what calculus is about in really kind of one sentence or a couple sentences, what would that be? Whether it's the integral, the area, or the derivative, how did we get those? How did we come up with derivative slope at one point?
Infinitely smaller than large.
approximations that got infinitely better, right? I mean, think about this, and I know you've heard me say it. If I want to do slope between 2 points, or slope at 1 point, I don't know how to do slope at 1 point. But I do know how to do slope between 2 points, so let's do slope between 2 points, but let the 2 points get really close. And that approximation gets infinitely better, and I get the slope of 1 point. I don't know how to do area under a curve, but I do know how to do area of a rectangle. So let's do area of a bunch of rectangles and let them get more and more, let their width get smaller and smaller, until I get an approximation so close that it's the actual area. This is the same thing. I don't know how to do the area of a curve, but I do know how to do the area of a straight line. Find that distance. So how about if we did an approximation using straight lines and let that approximation get better and better and better? Right? I mean, the same idea. And again, all of the things we are doing in chapter 7 have that same idea. What we just did with area between curves, same thing. Don't know how to do the area between curves, but I can do a rectangle, so let's let the integral add up all the strips of area. But it was very closely related to what we did before with area. But look at this. So what if I say, well, let's just, let's find the area between there and there. Or excuse me, not area, length. Let's find the length from there to there. Now, is that a very good approximation? No, it's really bad. Okay? As we know, when we do fewer, we don't get a very good approximation. So what would be better?
2.
Thank you for playing along. 2 would be better. Find that length plus that length, 4.08, but it's probably what? An underestimate. So what would be better? You guys are awesome. Thank you. 3. 3 would be better. Yeah. 4.207. Well, if 3's good, 4's got to be better. Okay? So there's the idea. So 5, 6, 7, 8. You look down here at the approximation. What's that? Yeah, that's kind of, what you had in mind was those sides. I got it. Yeah, absolutely. Because there's 8. I stopped at 8. I knew. I was thinking of the arc. Okay. Keep going. Keep going, and you see the digits start to zoom in there. You got 3.0. Okay, now it's, probably going to be at 3.05 something. And we're getting closer and closer. We got 63 of them. But we could keep going and keep going. Measure all those little segments. Now the question, okay. All right. The other class we went to 106.
We gotta beat them.
So we'll go to
Yes.
106. All right. So that's the idea. Now, the question is, how do we turn that into a usable form? With derivative, we had to take the slope formula. We had to do f of x plus h minus f of x all over h. The limit as h went to 0, and that was our formula. For integrals, we had to, of course, learn how antiderivatives fit, and we also had to do the whole sigma stuff. F of x sub I times delta x sub I, that makes area. The sigma adds up those areas as we let n go to infinity, and then we said that's the integral, and that's what the integral does. Now that we know that the integral is an adder, we can now set up an integral that will add all of these lengths. So we need to develop a formula that will give us these lengths, and we need to develop it in integral form. So here's what this will look like. So we'll go to this PowerPoint that I made up. Okay, maybe I stole it. This, I really like this. I don't know if you guys noticed this on the PowerPoint yesterday. This Greg Kelly is who I stole it from. And the photo yesterday of the arch, remember the arch? And it said photo by Vicki Kelly. You see what it says down there? Photo not taken by Vicki Kelly. I just noticed that this morning. I thought that was good fun. All right, but anyway, so here we go. What's that? What? All right. So in other words, okay. So here we go. So if we want to approximate this curve, we can take a short segment, okay, in a small space, and find that length. Now we're going to call that change in S. Okay, S is going to be our length of our curve. Remember in trig class, S equals R theta. That was arc length. Okay, we're going to use S for the length of our curve. Okay, so that red length is S. Now to find out, we'll make a hypotenuse of a right triangle, because that'll give us. Listen now. That'll give us our delta x which we're going to need. We're going to need a dx piece for our integral. So we got the change in x, change in y, and the length of the curve would be on the hypotenuse. Okay, that's how we find length in the coordinate system anyway, the old distance formula. Basically, that's what this is. Distance formula, of course, distance formula is just Pythagorean theorem. So, if we take dx squared plus dy squared, that would equal ds squared. Now, ds is the length that we're trying to, okay, that's the change in s. Okay, s is what we want for a length. Okay, so we square root both sides and we have this. Now, we want to add up all of those little s lengths to get our total length. So we're going to do the integral of both sides. Okay, the integral of 1 ds, that would just be s, that would be our length that we're looking for. It would be all the lengths added together, so that would be s. And then we have this. Now, we need to do some serious algebra to this because we need to get that dx out there. If we're going to have a usable integral, it's got to be the integral of something dx. That's just the way integrals are. They have to have that dx piece on there. We need to get that out of there. So it's going to take some algebra to do that. So here we go. This part you might want to write down. So we will finish that and come back to this. And I get a new page. We'll come back to the problem we were doing later. You might want to save a little bit of room for that. So what we have here is our length, s. That was from the other page. That was the left side. That was the integral of ds. That's just s. And that's going to be the integral of the square root, and I think it said dx squared plus dy squared. So what that is that's one length. That's this in here, this square root is the length of one of those little segments. And then, of course, the integral does what? Adds them all up. Okay, it adds up all the integral segments from A to B. Okay? But now this is not in a form that we can use because it doesn't have the dx piece out there. All right, so we're going to do some fancy algebra to this. What we're going to do is we're going to multiply inside the square root by a 1. It's going to look like this. I'm going to make a big, tall square root. I'm going to take my dx squared plus dy squared, put that all over 1. I haven't really done anything yet, okay? And then I'm going to times by dx squared over dx squared. Now it's all inside the integral. That's just a 1, right? So I just multiplied by 1, fancy 1. So nothing really changed. All right, now whenever you multiply two fractions, right, you can just multiply the tops, multiply the bottoms, right? Well, in this case, I only want to multiply the bottoms. So I'm going to multiply the dx squared, multiply and stick that inside there, right? Now once it's inside there, I've got a fraction with a single denominator. What can I do with it? Split it up. So I now have another big, tall square root. So now inside my parentheses here, I'm going to split it up, and what do I have? I have dx squared over dx squared plus dy squared over dx squared. Okay, so that's in my parentheses there. And then what do I have outside the parentheses, still inside this square root? I just have the dx squared, correct? The one that was on top, right? This one that was on top is still there. That one I moved in and then did that. Okay, now, a couple of things I can do here. Okay, I got my square root. Now, what's dx squared plus dx squared? Or over dx squared? That's 1. Plus, now, no, it's not same derivative because this literally is squared. I have dy squared over dx squared. Now, you remember like 3 squared over 4 squared, that's the same as what? Yeah, 9/16, I know, but that's the same as 3/4 all squared, correct? So dy squared over dx squared is the same as dy over dx squared. Oh, now that's kind of cool because dy over dx is derivative. That's y prime, right? Slope. Will slope be involved here? Will the length of the curve from here to here depend on its slope? Sure it will. Steeper it is, the more it would go up and maybe come down, and so it would be longer. So the derivative, it's not surprising the derivative's in there. Okay, now, you've also got this dx squared sitting here. Now, I've got two things multiplied in a square root. Here's another thing I remember about square roots. Square root of 32 is the same as square root of 16 times square root of 2, right? I can take and split a square root when it's multiplied. So I'm going to split this out as a square root of dx squared. What do you got? That's what I wanted. Right? I needed, that's the reason I did that whole thing, was to get a dx out there. Okay? So I knew if I got a dx squared under the square root, I'd have square root of dx squared. So that was the whole purpose of doing that fancy one. And I got the well, there it is. That is my formula. Now, most of the time it's written in another way. It's b from a to b, of course. Normally you see this written as 1 plus, instead of dy dx, or it could be y prime, or sometimes we have our function given as f. So a lot of times you'll see this written as f prime of x dx, and that's squared. Don't forget that that's squared. Dx. That's probably the most common mistake people make, is when they do this formula, they forget to square that f prime. Okay? So, if we follow this back now this is just something you have to memorize. Like average value formula or something. You just have to memorize this length of a curve. But if we follow this back again, remember where this formula comes from. This was just algebra that got it in this form. Where it came from was the integral was adding up an infinite hypotenuse lengths. Because that's what this was here, with those little red lengths. Okay? And this integral just added them all up. All we did was rearrange the algebra into this form. Okay? Now, to be really technical, we should have done it as sigmas, and n went to infinity, and that's how when dy dx goes to the derivative, because as n goes to infinity and so forth. But that is our formula. So let's go back to our problem. Okay? And the problem says find the length of the curve from -1 to 1.5 of y equals 4 minus x squared. We would write the integral from -1 to 1.5 square root 1 plus, okay, the derivative up here is -2x. -2x is all squared, which of course would turn that into positive, dx. Type that into your calculators. Give an exact answer or just a decimal? Decimal. So that thing must not have had an antiderivative. What was it? 30526 something something. Okay? Now, if we remember back to our other picture here, the actual length, 4.30526, we were getting pretty close. We were within 3 decimal places with 107 subdivisions. And go back to the PowerPoint real quick. Okay, they went through there. There's their formula. Now, they do another problem, but it's very similar. It's a parabola. Whoops. A little crazy there. Okay, now, notice that they come up with the exact same formula because -x squared plus 9, that's very similar to ours. We shifted up 4. Theirs is shifted up 9. But it goes 0 to 3, so it's going to be longer. They're going to get a bigger answer. But their formula looks the same. The difference is the 0 to 3. That's what takes that into account. But this part didn't change at all. Now, something I want you to keep in mind, and I've said this before, and I'll say it again now. You might get a problem like this that says, matter of fact, you're going to in the homework, so I'll just hopefully answer the question right now. You get a problem that says, find the length of this curve using 5 right rectangles. Now, people read that question and they go crazy thinking, well, how in the world can I find the length of the curve using rectangles? Well, what's wrong with their thinking? The problem says approximate the length of this curve using 5 right rectangles. And they say, I can't approximate a curve with rectangles. What are they talking about? What's wrong with their thinking? What do you approximate with 5 right rectangles? An we're right, an area, but integral, a definite integral. Now, yeah, we've mostly thought about it as area, that's true. But really, if you think about our b minus a over n times f of blah plus f of blah plus f of blah, right? That doesn't really, I mean, yeah, it means area comes from area, but it doesn't have to have the meaning of area. It's just numbers, right? A definite integral is just a number. This thing right here is just a number. 60 is a number. What's it mean? Depends on the problem, right? Could be how fast you're driving. Could be how much money I have in my pocket. Probably not.
60 cents.
60 cents, yes. You know what I mean? It's just a number. So when they say find the length of this curve using 5 right rectangles, what they're saying is find that number using 5 right rectangles. Well, you use 5 right rectangles to find an integral. So the first thing you have to do is what? Set up the integral. So when it says find the length of this curve using 5 right rectangles, they're saying set up the integral that will find the length of this curve. So here we go. Boom, get to here. Now, you would think of this as your f right here for your f notation in your R5 approximation. Now, they may have called this f up here. Well, you'll think of, when you get to here, you'll think of it as this as your f then. Right, and that, hopefully that won't confuse you. Okay, this is the function we're finding the length of the curve of, but this is the function we're doing the integral of, right? If you type this into your calculator, right? If you go to your calculator and type this in and hit enter, your calculator is not thinking, oh, I'll bet he or she is doing the length of the curve from 0 to 3. You know, well, it's a calculator, it's probably not thinking anything. But it's, okay, but if it could think, it would think, gee, it would, you know, as it was doing it, it would think, gee, I wonder what that integral is that he's doing. I wonder if it's an area. Is it the area under that? Sure, it could be, right? Whatever this answer comes out to be, 9.7. I think you even have a question in there today in your homework about this. About here's an integral. What could this mean? What could mean area under this curve? Or as we just learned now, this integral could also mean the length of this curve from 0 to 3, right? The integral itself is just a number. What it represents depends on where it came from. Okay? So when we first learned about integrals, it was all just about area under a curve. Well, now we've done yesterday area between two curves. We got an integral. Okay, now we got an integral that means length of a curve. Okay, length of that curve from 0 to 3. The integral is this. Okay? So if it says use 5 right rectangles, you don't do that until you've got your integral set up. And what if it said 20 right rectangles? Use that area program on your calculator, right? Remember, that rule still applies. And you'll have to do that on your homework, so we'll get that area program up and going again. Okay? So if it wants you to do 20 right rectangles, you use that program on your calculator. Okay. So, that is what we've got. I really think that's all. Oh, one other thing. I kind of want you to type this in just for the heck of it. They give one more example here. You can see it's a few years old. It's got the TI-89 stuff in it. Oh, and then they check this. That's kind of interesting. They take a straight line and that red line there and do a Pythagorean theorem and see it's about 9.49. And sure enough, the blue length is a little more. 9.74 would be a little longer. Okay, makes sense. Here's another one. It says, if you get a difficult derivative, go ahead and let the calculator do the derivative for you. Okay? And they give some directions with the T89. Okay, here's an interesting problem here. So find the length of this curve. Well, gee, that's easy. It's a circle, right? What should be the length of that blue? Circle radius 1. Half the circumference. What's the circumference? Circle radius 1. 2 pi r. So radius 1. 2 pi. This should be pi. So the length of that should be pi. Well, what would you have to do to set up your integral? You'd have to solve for y. Okay, it's a top half. Then you'd want the derivative of that, which you could do on your calculator. So you might, while I'm passing out this thing, I do, you might want to try it, it's up to you, but from -1 to 1, 1 plus the derivative of this, right? A little more, I mean, certainly one we can do, but squared, see if you get pi. Should. Okay? All right. So, on your assignment sheet, there's 2 lines today. Okay? There's 2 lines today. One line is in the book, 7.1. Now there are 2 lines right together, so those are the 2 to do. 7.1 is in the book, and it's length of the curve stuff, like we're just doing right here. Okay, the next line says LH. I've got a new LH packet for you. Killed a lot of trees this week. We got a new LH packet. It's a little thicker because I ran off the whole chapter for you. So you've got the example exercise and everything. The LH problems are yesterday's stuff. Top minus bottom, right minus left. Area between 2 curves. So you get some practice on those again. Larson Hostetler. Not the character on Big Bang Theory.
Probably the same thing.
It could, yeah. Maybe that's, I could be where they got those names, I'll be honest with you. You're probably right.
No.
It would make sense.
There's probably somebody named Hofstadter or something, some famous physicist. Now I'm gonna have to look that up.
Wait, are we gonna try and figure out the other thing?
What one?
One that Zach said at the beginning?
I thought about it.
Oh!
What if you just keep the 2 f of x values the same, and like if you straighten it, you could just make it into like a trapezoid sort of shape?
But I still not following the,
I don't do this.
Like if you just like
oh wait, it wasn't on this, was it?
just like straighten out the curve that's in the center, but keep the base value the same and the f of x value is the same length, and then you just straighten out the curve.
So, I'm just not very smart.
That's obviously the mistake.
So this is, and maybe this doesn't matter, this is 1.5. And this is like 1.75, yeah, it'd be nice if we had a little nicer number, but that's not too bad. Okay, now do what? Now what? Okay, what was the trapezoid? Go ahead, Wyatt. I think you're on.
If you keep these lengths the same, and you just like bring both of them out, and then just make that the middle. And once you find the area, then you can use the area. To
Now, what do
solve
you
for
mean
this.
bring both of them out? That's the part I'm not seeing.
Like you keep this length the same, and you just swing it out this way. If you keep it the same, and this one do the same, and then the curve just becomes this.
But there's no way to find that length.
That becomes your whatever.
But then you wouldn't have this height either, would you?
Just keep the height of A and B and switch it. Do a trapezoid, the height.
Now, why? Okay, hold that thought. What would this length be?
That's the f of x value.
Yeah.
You just
That's that value of
yeah,
3.
you just swing it out.
So this would be 3, and this would be the 1.75.
You keep the base the same, but if you find the area, then
This would be 2.5.
And that
But
must
now
be
the
same
problem
area.
is that's not a trapezoid
what if you
Be-
average
because this is not parallel.
if you average the 2 f of x values?
Okay. Now that might be along the lines of what they were saying earlier. Maybe. Might be the same thing. So if I average these 2 values, been nicer to have something little. What would that be? That'd be 1.25, so 0.6, so that'd be 2.375
Be the new height.
would be this height. Now, we need this area, right? Somebody got that for us? It'd be the area.
The area's down at the bottom, isn't it? Oh, no,
Um,
that's the arc length.
Yeah, that's the arc length. And so this would be -1 to 1.5. What's that number? That would be this area, right? That's what we were talking about doing. Somebody got that for me?
8.546.
okay? So that's that area. So then we were saying make a rectangle of that height. So basically, if you say take this and divide by that, right? Would that be have to be this length then? Correct? If this is a height, and we want to have that equal area, so take that divided by that, and that should be this.
Yeah, see if it's 4.3.
It's 3.59.
3.59.
But you would have to adjust the curve for the
What do you mean?
The derivative has to be some.
like if you're gonna
Well,
move the
see,
one.
I was thinking if it goes up steeper and it still comes down to those same 2 points, we'd have a bigger area. So I thought, well, this would grow. We divide by this constant, and so that 3.59 number would grow, as so would length of the curve. Are they the same though? And that, they might be related, but I'm not sure they're the same.
Well, like when you move the 1.7 up, part of that curve needs to go up too.
Where are you at now? Would that move what up? This?
Yeah, and then where it would go is when the 3 moves down. But then it'd still be a curve. It would still have that top part, and you'd have to spread it out. But once you spread it out, like Wyatt was saying, would it then, like what would,
Well, I'm still not following what your spread it out means. I mean,
like what Wyatt did before, where you
but they would.
moved it. But yeah, but if you average them, then they'll be parallel, won't they?
But when you get to the end, like even after you stretch it out, I just thought about this. You wouldn't have the height. You'd have to have that base length to find the height. So technically, you'd have to solve for the length of the curve to get the height anyway. So you'd have 2 unknowns at the end.
That's what I mean.
I would draw some.
Yeah, absolutely.
Well, that's the length of the curve, right? Let's just pretend that that has the same area of that. So if you do what you're doing with this thing going through, you get the same area divided by the same length.
And it's clearly a
Yeah.
longer arc length.
So you'd have to do something with the slope no matter what.
Here, throw me that mark. Does that make sense what he's saying? I mean, you could draw some curve up and down there. Surely that you could draw many curves there
It would have the same.
that would have the same area as that one, that would have different arc lengths. And so just using division and averaging doesn't seem like it would get it there without having the slope in there somewhere. All right.
Some of it, like physics, some of the physics stuff might.